14.3 and 14.4. And I actually just called the title of this pH and pOH. You'll know what I mean later. But measuring acidity of acid or base solutions. And on the worksheet, I want you to do number 1 and number 2. Then you can either do number 4 or number 36. Now let me tell you, if you want to be like, hey, I'm going to make a 5 on the AP, do 36, okay? 36, you can do it. It's not that bad. When you see the answer key later, you'll realize if you need help on it. But everybody, you ought to try it. But it's just a little time-consuming. Sometimes on the AP, they ask a time-consuming question like, oh, gotta do this. Like it has some stoichiometry and stuff in it. Conversions, I'd say. But it's not that bad. It's just a little bit, it's not much more difficult than 4. I mean, if I were doing them myself, I could probably do them about the same amount of time. Maybe 36, maybe slightly longer. But you'll see that if you can do 36, you can do 4. Of course, I've been doing it, for whatever long time. But it is, okay, I'm talking too much about that. You can just decide what you want to do. You can do number 4 if you can try 36, go to 4. And they both require a little bit of work, a little time. But I think number 36 might be more worth the investment. Okay. All right, here we go. And like I said, you'll all see the answers to this anyway at some point. You can study, see it. Okay, so the notes, I have a lot of notes here. And it's not going to really be, it is a lot of material. It's not going to be that much. One thing good is we're now getting to calculation. Looking for some chalk. And I didn't mention to you that this chapter on acids and bases is, I don't know, it has a significant section that is not any math in it. Like what we did before, so far we haven't done any math. And there's going to be some more things like that in the future. Little essay, equation kind of stuff. So maybe a little bit more than some chapters are. But oh well, that might be good news if you don't like the math. But now this is math that is not too hard. Okay, so it mentions in 14.3 that pure water, and I told you this before, is not acidic or basic. In water, there is a species H+, which gives you hydronium, and there's also the species OH negative, hydroxide. H+ is acid, hydroxide is base. It's okay to write that equation. That's true. A water molecule. Okay, so in a container of water, I don't have pure water here with me, do I? I don't think I do. But in water, well, it doesn't have to be pure water. It could be a solution. Doesn't matter. But all the water you see in here, most of the molecules in that container are intact. They're H2O molecules. Okay, they're not broken up. They're not dissociated. The majority, almost all of them, are H2O, H2O, H2O. But what you might not know is some of them are Some of the water molecules are broken up. Okay. And so that since they break up into H+ and OH negative, you have some H+, some OH negative. So everyone that breaks up gives you one H+ and one OH negative. I'll just do 3 of them. Okay, so now why do they break up? Well, the real reason why they break up is because they bump into each other. Temperature. Your temperature increases, they hit each other, and it breaks one apart. So now, the other thing you need to know, and I've told you before, H+ in water isn't really just floating around by itself. It's okay if you make a symbol and show that and imagine it. And this equation is okay. AP even uses this sometimes. But the better form of this equation is to say that 2 H2Os give you H3O+. Okay, I kind of interrupted myself. It's okay to write H+, OH negative. This is used by AP a lot. But in reality, H+ will join on to other water molecules. Really not just one, but several. It's kind of a weird configuration. But the way we write it is, an H+ in water gets attracted to a water molecule, and they make, it's not really a reaction, but they make H3O+. So H3O+ is another way to write H+ aqueous. Okay? It's just another, that's aqueous too. Another way to write it, a better way is to write H3O. So 2 H2Os give you H3O and hydroxide. And a better way to write that, and I've shown you this already on my in a past lesson, is to have 2 H2O molecules. That way you can really see, oh, they bump into each other, and one of them breaks apart. One of them, whoever's the weaker one, you broke apart, haha. So one of them becomes H plus. Let's just say that one breaks apart. That one becomes H plus OH negative. This one joins on to the H plus, okay? Or vice versa, H plus joins onto it. So this is probably a better way to write it, to understand what's really going on. Okay, but anyway, you're going to see all that. That's how you'll see it written down. All right, so as I've told you in the past as well, if hydronium molarity is greater, okay, first of all, let me do this. I'll talk about greater in a minute. I erased my diagram, but remember, it had 3 H pluses and 3 hydroxides. And then everything else was just H2O, 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 H2O. You can zip it back, roll it back if you want to see that. But almost everything was water, H2O. The majority, like almost 100% of the H2O molecules not broken up. But some broke up. But notice, of the ones that broke up, they're equal. The positive and negatives equal out. H plus OH, H plus OH, H plus OH. So the molarity of this, if they're the same, then we say the solution is neutral. It's not acidic and it's not basic. Now, if the H3O plus was greater, now how would that happen? Well, I have to put something else in there besides water, like acid, HCl. If I add it to the water, now when you add it to the water, you're upsetting the balance. And now, I have a whole lot more H plus, H plus, H plus. Now it is going to be greater than OH negative. That means it's acidic. And you already know this. And so if it's less than, it will be basic. Or another way to look at it, if OH is greater, then it will be basic. If OH is greater than H3O plus or H plus. Okay, that's an easy thing. I think you got that. That's the important part of that. Now, okay, for the equation, there is an equation, not equation, I'm trying to say, an expression for this reaction, and you've seen it as well. H2O to give you H plus OH negative, or H3O to give you, okay, either way. And here it is. It says the Kw of water is equal to the molarity of H plus times the molarity of OH negative. That number at 25 degrees Celsius, okay, remember 25 is your standard temperature. So a lot of times you'll see at 25 degrees Celsius, Kw of water equals 1.0 times 10 to the negative 14. And I even showed you this before. It's 1 times 10 to the negative 7 of that, 1 times 10 to the negative 7 of that. Hey, I noticed that there was a misprint. There was something in your notes that wasn't good. Okay, I know what it was. It was, if you want to go backwards one page to 14.2b, it says H2O Ka is 1 times 10 to the negative 14 Kb. No, that should be negative 7. That's goofy. And you know what? You don't even have to worry about that. But anyway, you don't have to worry about that at all anyway. But it was back on that page. That's wrong. I don't know where I copied that or copied and pasted, didn't fix it or whatever it was. Okay. All right. But that was one page backwards. All right. So back to this again. What did I do with my page? Okay, there we are. Okay. So the water dissociation constant is Kw is that. 1 times 10 to the negative 14 at 25 degrees Celsius. Now, what would happen if you changed? Do I want to talk about that yet? I might not talk about that yet. No. Oh, as temperature changes, Kw will also change. Think about it. As temperature changes, the H2O molecules that bump into each other. H2O molecules at room temperature pretty much bump in and make this true, this math relationship true. It'll be 1 times 10 to the negative 14 when you multiply those. So if you have warmer temperature, warmer than that, are molecules of water going to bump more frequently or less frequently? More forcefully or less forcefully? They're going to be more forceful and they're going to be more frequent. That means more of them will break up. So because of that, the Kw value will get higher. Okay? Like it might go up to, I don't know what temperature, but at some temperature it might be 1 times 10 to the negative 13. And you may get 30 degrees Celsius. So this has not been done on the AP to my knowledge, or maybe it has been. I heard it was done at least sometime years ago, and they love to bring things back from the dead. So if for some reason they ever said there's a problem where you use that equation, you'll know, and they tell you, oh, at this temperature, kW is 1 times 10 to the negative 13. Well, make sure that you know, or whatever it says, negative 18 or whatever, make sure that you use that number for kW. But you can pretty much bank on the majority of all the questions on the AP, probably all of them, it's going to be 1 times 10 to the negative 14. It would have to be a special situation to not be. Okay. All right, and we're not even doing the math here yet. Okay, so, all right, and now that I say that, here comes the math. Okay, so for letter A, this is what I just kind of wrote on the board for you. On the next page, example A, state or calculate the H plus OH negative concentration in each of the following, identify as acidic or basic. All right, so you're going to find this to be, I hope pretty easy. All right, letter A. So if you have number 1 on letter A, a solution is in a hydroxide 1.0 10 to the negative 5. Hydroxide equals 1.0 10 to the negative 5 molar. Okay, so what is the H plus and the OH? Well, the H, and we're going to assume all of these are at 25 degrees Celsius. So the OH negative, we know that already. Okay, we don't need to know that. We don't need to figure that one out. And so to find the other one, kW is H plus. Let me see. Did I write it? Yeah, I did write it that way. I think this is how they write it on the AP. I think they actually put OH times 8. They put that one first. It doesn't matter. But if you ever saw H3O plus times OH, it's the same thing. Don't be afraid of that. If you saw that, it's the same thing. Okay, so anyway, figure this out. So 1.0 10 to the negative 14 is equal to the H plus concentration, molarity, times 1.0 10 to the negative 5. No ice boxes in this part, not yet, not today. 1 times 10 to the negative 14 divided by 1 10 to the negative 5 is 1 times 10 to the negative 9. I guess I should have known that anyway. Just subtract the exponent. Negative 14 minus a negative 5 will be negative 9 equals H plus. So, all right. So now, is it acidic or is it basic? Well, which one is greater? 10 to the negative 9 or 1 times 10 to the negative 5? Remember, 10 to the negative 5 is a bigger number because this means you have 0.00005, that's 0.000000009, whatever, 01, whatever. I'm sorry, I'm saying I'm wrong and doing it real crazy. That's 0.00001. This one is 0.000000001. Yeah. So that is a bigger number than that is. And you know a negative 5 power is a bigger number than negative 9 power. So you should know that anyway. All right. So, what is the next thing to bring up here? So is it acidic or basic? So since OH is greater than H plus, so it is basic. All right. Now, what if you have a solution that is 1 times 10 to the negative 7 in, that's an easy one, you almost could probably know that one, hydroxide. I didn't need to erase that. If OH negative is 1.0 10 to the negative 7, well, we already know that H plus is going to be the same because H plus, OH negative have to give you 1.0 times 10 to the negative 14. You know that, right? 1.0 10 to the negative 7. So it must be 10 to the negative 7, okay? Oh, well, I hate to write all that out, but oh, well. It's the same thing. When you divide that, you're going to get the same thing. 1.0 10 to the negative 7 molar is the hydroxide. Because it's, negative 7 give you negative 14. You add exponents when you multiply. So it will be neutral, because they're equal. OH negative equals H plus. And by the way, even when I'm going quick and being lazy about it, but you still have to brackify. You got to show the brackets. Okay, that means the molarity of OH equals the molarity of H plus, so it is neutral. This is what I mean about how you can just write it. You don't have to use complete English phrases. You can use little broken parts of phrases to do it, and symbols. OH negative equals that, so it is neutral. That would be okay on the AP. You wouldn't have to say the molarity of the hydroxide, or the hydroxide concentration is equal to the concentration of hydronium. You don't have to say it that way. All right, number 3, a solution in which H3O plus is 10 molar. You know, I hate to keep writing this down over and over, but oh well. But I should have kept the equation up here. I don't know. Sometimes I do it the other way around. H plus times OH negative equals 1.0 10 to the negative 14. So if your hydronium, remember that is hydronium, it's the same thing. In fact, if the question said that on AP for calculating it, then I would put in H3O plus into my formula, just so they know that you know that is 10 molar. And I better put a dot after that, times OH negative, 1 times 10 to the negative 14. So OH, this divided by 10. 1 times 10 to the negative 14 is going to be 1 times 10 to the negative 15. 1.0. All right. Okay. B says, okay, there it is, 60. At 60 degrees Celsius, Kw changes to 1 times 10 to the negative 13. Is this following reaction, they call it auto-ionization of water. That means when H2O plus H2O bumps into each other. Is that reaction endothermic or exothermic, and explain why or why not? Well, this little question, just something they pop in there for you. Since the Kw value goes up, it increases, then what that means is that this reaction to give you H3O plus and OH negative, is it endothermic or exothermic? Well, if you increase the temperature, it goes, the value of K goes higher. Kw, that means your H3O, Kw goes up to 1 times 10 to the negative 13. It increases. Kw increases at higher temperatures. Increased temperature causes Kw to increase. So what does that mean? So think about Le Chatelier. Where would the heat have to be there? Heat would have to be on this side, energy, the joules or kilojoules, we'll say. Because if I add more heat, then that number gets higher and that number gets higher. So therefore, if that gets higher and that gets higher, then your Kw will get higher. So it must be on the left side. It should be equals. It should be plus. Heat plus this gives you that. So you increase temperature, Kw gets to be a higher value. You decrease temperature, and it will be a lower value. It is good to be able to explain that kind of question, but I don't know if that particular one would pop up. Okay, and then number 2 says, well, calculate H plus and OH in a neutral solution. You would just, I'm not gonna bother with that, but it would be 1 times 10 to the negative 13, and each of them would have to be x. Just say x times x equals 1 times 10 to the negative 13. Let them both be the same. And then 2x equals that, so divide by 2. So it'll be 1 times 10 to the negative 13 divided by 2 is 5 times 10 to the negative 14, actually. Kind of weird. 5 times 10 to the negative 14. You're not going to see that. Okay, I don't think you will, but you can write it there. OH negative times H plus, let them both be x. X is H plus. X is OH, because they are equal. They'll still be neutral at that higher temperature. But x times x gives you 1 times 10 to the negative 13. So that means it will be what I just showed you, 5, 10 to the negative 14. Okay, finally the fun part. Now this is the big stuff. We're getting to the pH. And that right when we get to this, I'm going to have to stop and be... I'll better just continue this in a minute. Otherwise, I'm going to go nuts. I always try and do 100 things at once. I know I'm trying to squeeze this in between a class right now, so I better start the other one. But I'll show you the part 2. It probably won't be about 10 10 or 15 more minutes. I hope this is a short lesson. We'll just see. We'll try it out. All right.